Okay, hi everyone. So we're very happy today that we have Gereon from NTNU in Norway, who is going to tell us about geometric Hodge filtered complex cobordism. Gereon, please.
Thank you very much for the introduction. Thank you very much also for the nice invitation. It's a pleasure and honor to speak in your seminar. I'm trying to, from afar, follow the amazing work that you're doing over there. It's very hard to keep up because you're producing so much interesting stuff that I don't think I was able to follow like 10% of what you're doing. Well, anyway, but yeah, so that makes me also quite humble with respect to what I'm going to talk about today, because it's like started a long time ago and it's like a long, slow process for me to produce any even partial results in what I'm doing. Okay, so what I'm going to talk about is a version of differential extension of a cohomology theory, but taking into account the Hodge filtration when you're working over, when you're in the world over complex manifolds instead of just smooth manifolds. So I assume that most of you have already seen these differential cohomology theories, and so you will probably have like your own way of motivating why we would like to study them. And there are probably well, there are many motivations for doing that, and probably better ones that I'm going to choose for today. But I hope you nevertheless bear with me with the story that or the starting point that I will pick for my story, and then try to build up to the theory that I'm actually going to introduce then eventually. Okay, most of what I'm talking about is, all of what I'm talking about is joined with other researchers, and the first part will be with joined with Mike Hopkins, and the second part be joined with a student of mine, House, and I hope I will remember to give them credit where it's due. Okay, I'm a little bit under the weather because my son didn't think it was a good idea to sleep tonight, so I didn't sleep very much. So I hope I will remember everything that I was going to say. Okay, so let's start. Oops. I can't. Let me see. I can switch to the next slide. Is that because you're recording, or?
I don't think usually it's related. Is the cursor not working?
Oh, now.
Oh, here you
do you see now the next slide? Yeah.
Yes.
Okay. I'm sorry. So let's start with a very classical and well-known situation. And of course, I'm aware that you all know how to do these things, but I would like to just use it as a starting point for the story that I'm going to tell. So let's assume we're trying to evaluate the integral where we take a polynomial f of x of degree 3. Let's assume it has simple roots, and we take the square root, and then we take 1 over that square root. And we want to evaluate it, let's say, from 0 to some parameter t. And so, of course, you all know that there's not a simple, usually there's not a simple formula for doing this, but we have to invoke, or it's a good idea to invoke some geometry in order to study this question. So one modern reformulation would be to introduce a new variable y, and then look at the equation y squared equal to f of x, because remember, we wanted to look at the square root of f of x. And then we would like to compute the integral over some differential, where we use our variables x and y, and we write omega for dx divided by y. And then we also pick a point P and a path in the space of complex solutions of this equation E. And so initially, maybe our question was just aimed for calculating this integral over the real numbers, but as you all know, if you want to do this in a systematic way, then it's a good idea to keep track of or to look at the complex numbers in order to keep track of the signs of the square root. Okay. So But by doing this, we pay also a price, or there's a significant drawback because now the integral, so this number I of p depends on the homotopy class of the path that we chose. Okay, so what this really gives us is a function that is defined on the universal covering space of E of C. Okay, so this, what we just wrote down, so associating a point P with this integral gives us really a map from the universal covering space E of C tilde to C. And you all remember that then Euler showed that actually there's a way of defining a group operation on the points of E of C, and then this map becomes a group homomorphism. Okay, but what can we say about or is there still something that we can say about associating to a point P in E of C and then associating to it the complex number using this integral? Okay, so we just learned that this integral depends on the homotopy class. So let's study then the path or the fundamental group of our space. Okay, so here I'm going to look at the first homology with integer coefficient instead of the fundamental group, and the reason will become clear in a second, such that the story fits nicely with how we're going to move on. Okay, so we all know that the space for such a curve, the space E of C is equivalent to a torus. So it looks like S1 times S1, and the homology is then just the product of two copies of the integers. Okay, so what we're going to do now is then we pick a basis. So two loops, gamma 1 and gamma 2, that form a basis for this homology. And then, well, first we just evaluate our integral, or we take our differential form omega, that's dx over y, and then evaluate it over this, or take the path integral over these chosen paths. And these two numbers, the two complex numbers, lambda 1 and lambda 2, they're called the periods of our curve. Okay, of course you all know this, but it will lead to eventually, hopefully, lead to something interesting. Okay, and then we can observe that now our map sending a point P in E of C to this integral becomes now a well-defined map if we mod out by the lattice that is determined by lambda 1 and lambda 2. And this quotient C modulo this lattice, that's isomorphic, or you can also think of it as the definition of the Jacobian of our curve E. That's the first instance of the for today of Jacobian. So it's in this case a complex torus. So it's a lot of geometric information, and this map is called the Abel-Jacobi map. And actually, in this case, this map is actually in isomorphism. Okay, so now why are we interested in Jacobians? So I would like to pick out one. Maybe you want to think for a moment like it's a random example. So there are plenty of reasons why we should study Jacobians. So let me pick just one example where they show up and might be useful, because I'm going to build up on this story then later. Okay, so I would like to look at Lefschetz's theorem of 1-1 classes, where we now assume that we take X to be a compact Kähler manifold. And you have all seen this theorem. Let me just remind you briefly of what it says. So we look at the set of isomorphism classes of holomorphic line bundles on X, and then we take a line bundle L, and then if we send it to its first Chern class, then this defines a homomorphism to the second integral cohomology group of X. Okay, and now one can observe or remember that this Chern class actually lies in a very specific subgroup of the second cohomology. And so here we use our assumption that X is compact Kähler, because in the Hodge decomposition, or the Hodge theory on the cohomology works nicely. And we all know that this Chern class actually lives in the subgroup of 1-1 classes. Remember, the 1-1 clauses, so if you take local coordinates on your manifold in order to calculate the differentials, and then you can split them into dz's and dz bars, and then you get the Hodge filtration or the Hodge decomposition on the cohomology by keeping track of how many dz's and dz bars you have. Okay, so in this case, one dz and one dz bar. Okay, and so Lefschetz theorem now says that this map is actually surjective. Okay, so I'm gonna now spend like a couple of minutes on how to prove this theorem, and I will not look at the most modern proof is, of course, it's just you write down an exponential sequence and it's just 1 or 2 lines, and then depending on how much knowledge you assume, then you're already done. But rather, I would like to look at Lefschetz's original idea of how to prove this theorem, because it will again introduce some players for the story that we're going to use later also. Okay. So for simplicity, let's assume that X is a projective surface, so it's embedded in a big enough complex projective space. And then we would like to look at a family of curves on X, and let's assume that they have a chosen common point P0, and we're gonna consider them as parametrized over the projective line. So for each point in CP1, we have one curve, and we put them all together in some way. Okay. So then we can again look at or define a Jacobian variety, or Jacobian for each of these curves. So T is our parameter in the projective line, and then we get for each T a curve CT here. And then the Jacobian is defined, so we take holomorphic 1 forms, we take the global sections, and then we take the dual, and then we mod out by the first homology again. So basically, it's exactly the same procedure that we did before for our curve E. Okay, and now we take the union, or like take the union of all these Jacobians and also collect them together, and let's call them this guy also the Jacobian of our family. So this is then again equipped with just a projection map onto the projective line. We just record of which curve we're taking a point in our Jacobian. Okay, this gives us the projection map pi, and it's actually a holomorphic map if we do this carefully. Okay, now we choose a curve D on X. So remember, X is the surface, so we take a curve, so something of codimension 1. And why do we do this? Well, I formulated the theorem for holomorphic line bundles, but actually, so divisors, or these codimension 1 objects on X, they correspond to starting line bundles on X. So if we can say something about these curves D, then we learn something also about the line bundles of X. Okay, so now we take our curve, our example curve D, and then we look at the intersection points for a given T with one of our curves CT in our family. And we just record these points, so let's call them P1 to PD. And then these points give us now a way to define an element in the Jacobian of our curve CT. So if we have taken our points P1 to PD, then we take a differential form. Remember, the Jacobian is a global section in this it's an element in the dual of the global section. So we could describe it by taking a 1 form, and then we look at so we want to define a map, and the map that we define is by sending it to the integral, where we take these points pi, take the sum over them, and we integrate over a path, and it starts in P0, and the P0 is this common point that we have chosen for all the curves. Okay, and so this map again is an instance of the Abel-Jacobi map that we're going to generalize even further now in a second. Okay, so what we produce now is if we do this for all t, so for all parameters, we have defined a section of this map. So we can take if you go from up downstairs and up again, then no, the other way, down, up, and down, no, up and down. So then we have the identity. So it's a section of this. That's what I'm trying to say. Section of the map pi. And such sections, if they are also holomorphic, then they're called a normal function. So this is classical theory, and I assume you have all seen this at some point, and maybe you would choose a different way of telling this or talking about this proof. But I hope you bear with me and accept that I choose this way to present it. Okay, so what we produce now is an assignment of starting with the curve D, and we attach to it a normal function. Okay, so now what do we do with this normal function? Now we can conclude the proof. So here we record this information, and now we're going to use Poincaré's existence theorem. So the name already tells us that it's a theorem that was proven a long time ago. It's basically a version of a more sophisticated version of Jacobi's inversion theorem. And it tells us that for every such normal function, so for every function that is a section of our map pi, we can actually find a curve D such that this normal function looks like this nu D that we get from a curve. Okay, and then there are two things missing for a complete proof of the Lefschetz 1-1 theorem. So first is we can associate to every normal function a cohomology class, and it has actually a Hodge type 1-1. And it's such that if I have the normal function that comes from a curve, then actually the class that I produce is equal to the Poincaré dual of the fundamental class of D. If D was a curve, we can also consider also its fundamental class. In homology, we take the dual, and that's our cohomology. Okay, and then the last bit is we have to show that every class of Hodge type actually arises as the cohomology class of a normal function. Okay, and taking then these two bits together gives us then a proof of Lefschetz theorem if we accept the fact that divisors correspond to line bundles. Okay, so that's the idea. So the idea of this proof. And now you could wonder, of course, there's not only Lefschetz theorem on 1-1 class, but of course also the more general question related to the Hodge conjecture, and why couldn't we use this proof in order to prove the Hodge conjecture? And so let's contemplate. So of course, I'm not going to say anything about the conjecture itself. I'm just going to use it as a motivation to look at the following situation, and let's see where this proof would not work, because a lot of the ingredients that we just developed, they actually exist also in a more general setting. Okay, so now I would like to look at the case again where we have access to compact Kähler manifold, and we look at now not a curve or codimension 1 object, but a submanifold of codimension P. Let's call it that. And then we can again associate to it a cohomology class Z, where we take the fundamental class. In homology, we take the Poincaré dual. And then we observe that this is actually, again, a Hodge class. So it lives in integral cohomology, and we get 2P, and it is of Hodge type P, P. So if we again keep track of how many DZs and DZ bars we have, then we have as many DZs as DZ bars. Okay, and we call those classes are called integral Hodge class. Okay, and now I would like to introduce another player that's I'm sure well known to you, because there's another group that will play a role for us in the forthcoming story, and that is the Deligne cohomology. And so this is this group here on the bottom. So D for Deligne, and we're going to look at it in degrees 2P. P was our codimension, and then we have a twist P as well. And then there's a map to cohomology, and it actually lands in Hodge classes in this particular degree. And so this map is actually surjective. And then we can also look at assign to our submanifold Z a class in the Deligne cohomology that I'm going to denote with the subscript D. Okay. And now, so we just learned that this map at the bottom here is surjective. So we could also ask then, what is the kernel of that map? And so this is the Griffith's, one way of defining Griffith's intermediate Jacobian. And so you can use this short exact sequence if you want as a definition, but I'm going to also yeah, you can use it as a definition, but there are also other ways of constructing this Jacobian. And it's the generalization of the Jacobian that we have just seen in the case of curve. Okay, so now you could ask, yes, so no, sorry. So first I'm going to say that now so since we have already now our classes Z and ZD, so is there also then a corresponding class in the Jacobian? And the answer is yes. So if we assume that the fundamental class of Z vanishes, then because the Jacobian is defined as a kernel, then if something maps to 0 here, then there is an induced element, or we get an induced map on the kernel of this short exact sequence if we consider like let's say the free abelian group of all codimension P submanifolds. Okay, and this map is let's call this invariant AG because it's an example of an Abel-Jacobi invariant. Or you can take this as the definition of the Abel-Jacobi map in cohomology. Okay, and now you could wonder, so why can't we then prove the Hodge conjecture using the same procedure? So now we have a candidate for the Jacobian for a higher dimensional manifold, not just for curves. We can also study the families of Jacobians parameterized over the projective line. We can study normal functions. So all that is there. Where the proof breaks down is Poincaré's existence theorem. So the key step where we go from something not algebraic to find an algebraic object. And of course, so here I used Hodge classes with integral coefficient. Of course, there are also other reasons why this, like principal reasons why this can't be. The proof that we just cooked up for the Lefschetz theorem can't work. And there's a conceptual reason why this can't work. And I'm gonna spend a minute now on explaining why this can't be the case. So the way we defined the class down here was we took the dual of a fundamental class in cohomology. And now if you think of cohomology theories in topology, so there are many more cohomology theories where you have a fundamental class. I mean, basically in every complex oriented cohomology theory, you can define a fundamental class. And the most universal one is the fundamental class in complex cobordism. So even if you don't know what complex cobordism is, which we denote here by mu, so for this part of the story, for the moment, what is important is that it is the universal among all the complex-oriented cohomology theories. So every fundamental class is, in some sense, is an image of this fundamental class in complex cobordism. And then from mu to P up here, we have a map down to cohomology, which is called the tomorphism. And the key observation is that this tomorphism, even though the cobordism groups here, they're much bigger than cohomology groups, but the tomorphism is not always surjective. And so if we observe that if we have a complex submanifold, then it has a fundamental class in complex cobordism. And if we want to have and that has also then an image in integral Hodge classes. And so if you wanted to prove a surjectivity statement for all Hodge classes, then we would also need that the tomorphism is surjective on these classes. And okay, so this doesn't even work then for when we look at a complex submanifold. So we have something smooth if you think of the algebraic analog of this question. Okay, so there's some fundamental obstruction here that keeps us from finding a submanifold for every Hodge class, and that's also very much related to the work of Atiyah and Hirzebruch, and where they use the Atiyah-Hirzebruch spectral sequence to define obstructions for finding algebraic cohomology classes. And one way of in some sense, reinterpreting Atiyah-Hirzebruch result is using this tomorphism. Okay, but apparently, so now I've introduced the main players of our stories. Spent a good amount of time on it, but now we're going to look at hopefully something new and interesting. So we have just learned now that in order to study the geometry of a compact Kähler manifold, it's interesting to look at the link cohomology, to study its Jacobian and the Abu-Jacobi invariant, but also complex cobordism plays a role in this story. And this is the motivation for what will follow, because now we're gonna, the first goal now is to define a generalization of the link cohomology where based on complex cobordism instead of cohomology. Because apparently the link cohomology and cobordism and the Jacobian, they tell us something in the story, and we would like to exploit this. And this was also for me the motivating starting point, and for the joint work with Mike Hopkins that I'm going to explain now. Okay, let me very briefly now remind you of how we define the link cohomology. Of course, you have all seen this before, and either as the link cohomology or as a smooth differential cohomology by Chige-Simon. So you've seen some version of it. So, but one way of defining it is that we take a complex manifold, we choose an integer, and then we look at the complexes of sheaves on X. And then first we take a locally constant sheaf just given by the integers. Then we take the sheaf of smooth forms with complex coefficients that I'm going to denote by A star. And then we map this locally constant sheaf Z into the sheaf of forms by associating to it. So we take a constant multiplied with this scaling factor 2 pi I p, that's not important, and then take send it to constant function, locally constant functions, and then map them into all holomorphic, or in this case, smooth functions on the manifold, and then into forms. Okay, so that's this map, and then we can take the Hodge filtration into account. So we filter this complex by taking local coordinates, and then so since we use complex coefficients, we can then split them into, or choose a basis consisting again of DZs and DZ bars, and then we keep track of how many DZs we have and use that to filter this complex. Okay, and then we would like to form the homotopic Cartesian square and define a new complex ZDP as the homotopy pullback of this diagram. Okay, and this complex is called then the link complex. Okay, and then we can define link cohomology just by taking the hypercohomology of this complex in each degree. And so for every integer we can do this. Okay, so now I would like to take this diagram and use this idea in order to define a version for it using complex cobordism. And one remark is, so just by defining this complex as a homotopy pullback, then produces the short exact sequence that we just looked at in the slide before. Okay, so it just comes from a long exact sequence that we split into or cut off into a short exact sequence. Okay, so this seems like a useful way of defining the Lie cohomology. So let's try to copy it. And this is joint work with Mike Hopkins, and it's already like the starting point is already a while ago. And as I said, I work much more slowly than you do. Okay. So now we put us in the setting of instead of complexes or sheaves on one specific complex manifold, we look at presheaves of spectra on the whole side of all complex manifolds. And so you remember presheaf is just a functor on a category, so it's just a functor from complex manifolds with values in spectrum. It could also start with a simplicial presheaf, so with values in simplicial sets or with values in topological spaces. So there are many variations, and it's just one setup that we chose in order to formulate our story. And then we look at the constant presheaf that is just given by this one spectrum mu that, remember, stands or represents this universal theory complex cobordism. Okay, so that's now an object in this category. And then we look at, again, smooth forms, this A star, and then we need to pick some coefficients for our theory. And there I used the notation V star for writing mu star, so the coefficients of mu evaluated on a point. And then we tensorize it, we take the tensor product with C over the integers. Okay, so that is this complex algebra, or a graded complex vector space. We don't care about the multiplication. And H stands for an Eilenberg-MacLane spectrum functor. And I stress here functor because so yeah, if we plug in an X and take the forms on this specific manifold, and then so then we get a chain complex, and then we can take the Eilenberg-MacLane space or an Eilenberg-MacLane spectrum of this complex. And like, since this works naturally, this turns it into a functor. Okay, and so this replaces now the complex of smooth forms, the complex coefficient. And if you think of what is the cohomology or the homotopy related to this this bottom part, so this one, then it's, so for the Lie cohomology, it gave us, so just smooth forms without the coefficient gives us cohomology with complex coefficients. And if we take these fancy coefficients V star, we just get cohomology with coefficients in V star. So it's not for the moment nothing very spectacular happening. We're going to see that taking all these information together will produce something new. Okay, so then we choose an integer, and then we use again this filtration of our smooth forms. And since we have a graded coefficient ring V star, we need to adjust the grading and the filtration accordingly. And this is here the way how to do it. So we take in degree 2j, we take the filtration step P plus J. Okay, that's all, just to make it work nicely with the Lie cohomology and a potential splitting of over the rational. Okay, now there's a map missing. This map from mu to this bottom corner. And so how can we construct such a map? So we go from this constant presheaf just given by our spectrum to this Eilenberg-MacLane spectrum of forms. Okay, so how do we associate a form to this this guy? So it's actually, so it's an abstract way of producing this. So we take a map from mu to where we take the wedge product with the Eilenberg-MacLane spectrum of the complex numbers. So on homotopy groups, what we're doing is we tensor with C. And then we take the scaling factor, but it's not really important. Then we use that, since C is a field of characteristic 0, well, this actually splits into a wedge product of Eilenberg-MacLane spectra. So we have some form of equivalence to just Heidelberg lane spectrum corresponding to V star. And then if we think of V star as constant functions, then we can map it again into A star, into the complex of all smooth forms. And one might refer to this map as a fundamental co-cycle. You see that also in liquid. Okay, so, and I'm gonna get back to this map in a second. If you think that's a weird map, I totally agree. And we're gonna try to analyze it a little bit further in a second. Okay, so but now we take the homotopy pullback of this diagram and use this as the definition of a new presheaf of spectra that we call MUDP. And this is now the new gadget that we will use in order to define a new cohomology theory. And we do this by saying that, so we call these Hodge filtered complex cobordism groups in cohomological degree n, and with twist p for complex manifold x. And we do this by taking HOMs in the homotopy category of, or the stable homotopy category of symmetric presheaves. So the homotopy category of this presheaves of spectra. And then, so we consider X as just as a representable presheaf in order to throw it into our category. And then we add a base point, we take the suspension, and then we take all maps into the n suspension of this guy. So once you accept that this abstract presheaf category exists, it's just the usual way of defining a cohomology theory for space. Right? We just need to put it into the right setting. Okay, so now this looks like a very complicated, maybe it looks like a very simple and down to earth way of defining something. Maybe it looks complicated, but anyway, it does a good job, at least for some respects. Okay, so let's look at this. What are the properties that we get for our theory? Okay, so first of all, so here we still have the definition. We have nice pullbacks along holomorphic maps. So as it would, so it's a natural theory. So that's nice. That just comes automatically out of the definition of the construction. We get a multiplicative structure if we take into account not just one n and one p, but take the sum of all n's and all p's. And so then we should rather work in the category of presheaves of symmetric spectra in order to have a nice multiplication. But if we take care of all these requirements, then we also get a multiplication. So that's nice. And we get a long Z sequence induced just by the fact that this is defined as that our MUDP was defined as a homotopy pullback. And you remember that taking homotopy groups or cohomology or homology of a homotopy pullback leads to a long Z sequence. And let's just for a second look at this exact sequence, and let's look again at the special case of a compact Kähler manifold. We've already seen that this was an interesting case, namely here at the bottom we have again the short exact sequence that we studied for Hodge classes and Griffiths Jacobian. And now we have again a tomorphism that if we look at the elements in degree 2BP, then the map from MU to a singular cohomology induces a map from Hodge filtered complex cobordism to the Lean cohomology. So that's just we exploit the functoriality and the existence of the map from MU to HC. Okay. And then we can extend this to when we focus on the degree 2pp, we can define Hodge class, MU Hodge classes, which is a subgroup in all elements in the subgroup of A. I'm sorry. So this is a subgroup in MU 2p of X, And it consists of the elements that are mapped to Hodge classes in cohomology, basically. So there's not too much interesting going on that side, but well, we have this subjective map onto this subgroup. Okay, and now we can again ask what is the kernel. I can just use this as a definition of an MU Jacobian. And so yes, so we use this short exact sequence basically as a definition of this object Jacobian for complex cobordism. And if you wonder, well, how does it look? Well, you can compute it, or as at least as a real Lie group. If you don't consider the complex structure, then it's mu2p minus 1 of x tensor with R modulo V. So it's something that you can compute in principle. Okay, and this short exact sequence just comes from the fact that we have defined mu dp as a homotopy pullback. And so this is really a long exact sequence, which we split here on the left and right in order to get a short exact sequence. Okay, so it looks like this fits nicely into the picture that we have drawn before. Okay, so we also have long, or if you want, short exact sequences and can define Jacobians. Okay, so now, so this is one part of the story. And now I'd like to ask like further questions. What are other properties of this theory? So far we have used like some very abstract or like generic way of defining a new theory and exploited all the general machinery of homotopy pullbacks and spectra and so on. And it works nicely for a lot of respects, but there are also other questions that we could ask. And so let's get back to our list of properties. So we could also ask, well, is there also a push forward along proper oriented holomorphic maps? Right, that's a natural question to ask for cohomology theory. And in the work with Mike Hopkins, we only constructed a push forward for a refinement of this theory for smooth algebraic varieties, where we take some logarithmic a logarithmic refinement of this theory. And for them, we get by some abstract machinery also we get a push forward. So, but it only works in the algebraic setting. So you could ask, well, there should be a push forward for every proper holomorphic map, maybe together with an orientation. And another natural question, I think, is there any geometric way to describe elements in this theory? Because we started with this abstract machinery, but how on earth do you describe a concrete element? So you may think, so I guess we all have an idea of how this works, but in order to make this actually work on the nose and concretely, it's turned out to be harder work than I thought. Okay, so let's think of how could we interpret an element in this in our theory. So we defined a Hodge filter cobordism class as a map from X into this homotopy pullback. Okay, so what is the map into a homotopy pullback? We could think of it as the information of, first we take a map from X to MU, we take a map to the other corner, and then for a homotopy pullback, we don't need that this commutes on the nose, but there is a homotopy in the bottom corner that glues together the images of these two guys. Okay. Yeah, so and we could think of this homotopy then also as a map H into this bottom corner. Okay, so then you might think, okay, then we have now we know what an element in Hodge filter cobordism is. So we just take the triple of these three maps and just say, well, these are elements. And in some sense, that's of course correct. But if you want to write down a concrete map, this turns out to be a really challenging problem. More challenging than at least challenging. It was challenging for me. Maybe you would consider it as trivial. And one main question that I was wondering about was also, how can we keep track of the geometry of this this vertical map here MU that we defined by some very abstract arguments to smooth forms. So how does this map actually work? Okay, and so I'm going to spend now the rest of my time to give you a geometric interpretation and like some explanation of how we come up with a solution to keep track of the geometry, and then how to use this in order to define a push forward and then an Abu-Jacobi invariant. Okay, so now we set out for a geometric interpretation of our elements in Hodge filter complex cobordism, and this is joint work with my former student Knut Haus. So, okay, so we just figured out that we need to study this as the starting point, that we look at these three maps. So first of all, a map in homotopy theory from X to MU. Well, Quillen told us that this corresponds to a proper complex-oriented map of codimension n from Z to X. And Z, so X is let's say it's a complex manifold. But in fact, for most of what I'm going to say now, it actually doesn't have to. But let's say X is the complex manifold, but Z definitely doesn't have to be. It's only a weakly complex, which means that there's a complex structure on the tangent base. Okay, but in general, it's not itself a complex manifold. Okay, then we have more geometric information attached to this. We can also look at the stable normal bundle of our map F. That's the bundle on Z. Stable because we need to choose some embedding into some Euclidean space, and of course we need to make this independent of our embedding. Then we can choose a connection on our normal bundle. So that's a way of, you all know what a connection is, so let me just briefly remind you that it's a way of differentiating functions on a vector map. Okay, and now we need to choose some extra information, and let's go. So we need to look at a genus. Well, I'm a little bit sloppy with the notation, so I'm writing K for the multiplicative sequence that corresponds to the genus. So remember, a genus is a ring map from MU star to any Q algebra, any graded Q algebra, and here we take MU star tensor with C. And the map has the effect that it multiplies by 2 pi I to the P plus N on the two ends homotopy group. Okay, so there's some ring map that we need to choose. And then we're going to use this to look at a form that we built from our connection nabla F. And so we take the Chern classes, so the total Chern class of this connection, which is defined using some formula with the determinant and involving the curvature of our connection. And then we plug this into our multiplicative sequence. Multiplicative sequence, you remember, is a power series. So we just replace the variables by these Chern classes. And then we get an element K nabla F. Okay, by Chern-Weil theory, the classical Chern-Weil theory, we know that the cohomology class of this form doesn't depend on our choice of the connection. So it just gives us the characteristic class of the normal bundle. Okay. So now this K nabla F. So since NF, so the normal bundle lives on Z. So the connection also lives in forms of on Z. But we would like to have something that lives on X, right? And if we want to have some kind of description that only depends on that is associated to X. Well, what could we do? Well, we take the push forward of our form. So the push forward along F of this K nabla F down to forms or to something in X. Okay, so now this looks like now very much like a, well, we would love to say it is a smooth form and could maybe give us some hint of what this map, this vertical map could be. But of course there are several drawbacks, or like several things that we need to consider with this construction. So first of all, if we take the push forward along the map, a proper map, then what we get is only a current, not a form. So that's a bummer. And then on the other hand, we would like to take the Hodge filtration on the bottom left corner into account. Okay, so how do we do this? Or how do we remedy these two defects? Well, the next bit of information that we need to choose is a current H such that if we take the push forward of K nabla F down to X, which is now just a current, not a form, we take a current such that if we take the differential of H and take the difference, then we actually get a closed form which lies in the piece filtration step on our smooth form. And so you can show like this, the Rahm theory and Hodge theory that you can always find such a current. Okay. So now, yeah, I apologize for there are a lot of objects now flying here on this board. So let's recapitulate what we came up with now, what data we have chosen now in order to explain our map, because now we have all the ingredients for the geometric interpretation actually. Okay, so we would like to define now geometric Hodge filter cobordism cycles. So just in the usual way that when you define like complex cobordism using represented by these proper oriented maps over manifold. And the data we need is, so we have our complex oriented map of codimension n. We choose a normal bundle, a representative of the stable normal bundle. We choose a connection nabla F, and then also this current H, which satisfies this condition. Okay, and all these, so this information, this quadruple of objects together, they are what we call a geometric Hodge filtered cobordism cycle. And now we can define a new theory, which I also denote by mu npx, but to distinguish it without the d as a subscript. So it's these cycles modulo suitable bordism relations. Okay. So now we have produced a new theory. Well, why does this help us in order to study the theory that we just defined? Well, of course, we would wish that they are isomorphic. But now we are again back at the question, well, how do we compare this? The one is, so the right-hand side is, I hope you agree, is rather geometric. And the left-hand side was this abstract homotopy stuff. Okay, so now before I explain how we compare these theories, let me just mention that if you remember the story for smooth manifolds and differential extensions of homology theories, so think back of the work of Hopkins and Singer, of course, who did this for smooth manifolds and defined general differential extensions for cohomology theories, and then the work of Bunke and Schick, who showed then that who put up an axiomatic framework for such differential extensions, and then showed that they're actually all unique. So once you have a theory that satisfies these axioms, then you get an isomorphism between two such candidates. So you could then wonder, well, is there also a similar uniqueness statement here in the background? And so the answer is, well, there might be, but we don't know. So there are obvious candidates for writing down axioms for what a Hodge filtered extension of a cohomology theory would be. So if we not just do this for MU, but also for replace it by some other complex oriented cohomology theory of your choice, or K theory or whatever you like. But we are not able to reproduce the proof of a uniqueness theorem. And the piece that is missing is that we don't know, well, in general, so for the smooth theory, you would like to represent every, maybe So we like to represent the space or the spectrum that represents your cohomology theory using smooth manifolds, or at least approximated. And then, well, we can't do this using complex manifolds and holomorphic maps, as far as I know, at least not in a sufficient way. Okay, but I can get back to this question a bit, because I'm running out of time, and I have some more slides that I would like to explain. Okay, so the way we show that there is such a in fact an isomorphism is by introducing a third theory. And I will just very briefly say like how we do this. So the HS stands for, in the subscript, for Hopkins-Singer, because it's more similar to the way that Hopkins and Singer produced their theory. Okay, so there we have like an intermediate version which is both geometric but also has the homotopy flavor. So we look at the smooth maps and whatever that means from the standard n-simplex. And then here we could plug in, what I would like to write as a functor, we could plug in a complex manifolds, and then we go to the tone space of the universal bundle. Then we can actually, so on the tone space, there are universal, or there are also tone forms on this universal bundle. You could define them using the multi-equivalent formalism, or whatever choice you take for tone form, and that gives you, by pulling back this tone form, you get a map to these smooth forms. You have to take care of all kinds of compatibilities and make sure that whatever that means, smooth maps from delta dot into this. So there's a lot of things that you have to take care of, but this is the idea. And then we just filter this by the Hodge filtration, and then we define again a homotopy pullback. This is done now for some n, which is related to the m and l of the universal bundle. But they all like fit together into a spectrum, and then you show that this new spectrum is actually equivalent to this spectrum MUDP that we constructed earlier, and that induces an isomorphism. And then on the other side, why is this helpful? Because for this new theory, we can actually use the Pontryagin construction on the nose, and like by taking care of everything, all the smooth structure and the forms along the way, it actually works out in order to show that this is an isomorphism. There's a lot of details that have to be checked, but this is basically the idea for this isomorphism. And then what we get is an additive isomorphism. And so additive, I would assume that the isomorphism is also multiplicative, but the procedure that, or the method that we use only shows that it's additive for the moment. But I would assume it's actually multiplicative. Okay, now in the remaining 2 minutes, I'm a little bit slower than I wanted, so I'm going to hurry up. I'm going to tell you why is this helpful in order to define a push forward. Okay, so let's assume now we have a proper holomorphic map of codimension Q, and then we would like to define a push forward, so a map from the complex, the Hodge filter cobordism of X to Y. And the Q shows up here in the formula in two ways. Once in the cohomological degree, but also in the twist. Once with a factor 2 and once without. Okay. So what is we take our, oops. So now I wrote this. This is I wanted to write this without the D, but I forgot to. So we're using now the geometric interpretation. So you should take the D away. I'm sorry for that. Okay, so a Hodge filter cycle consists of this data, and then we associate with a new cycle by some formula where we have to take care first. Basically, it's just the geometric push forward of in cobordism, where we have to choose a normal bundle, a representative of the normal bundle of G and a connection. And then, oops, we need to choose also a current. And for this current, we use this, we need this formula. So don't worry about the details. So what is, so there's some formula that in order to make these things work, and it's more complicated than you would wish. But there's some interesting information that we should keep track of. So there's some things that we need to choose in order to make this this series. So there's the normal bundle, the connection, and then some form sigma G, which lives in A minus 1 of X, such that K nabla G minus D sigma lives in F0 of A0 X. And remember, so this seems like an obvious, like an empty requirement, but remember that we have here coefficients, graded coefficients. So it's actually a condition. So this choice, we could record this as saying that this is an orientation that we need to choose in order to construct this map. And now you could, well, making one such choice is good, but is this independent of, like, how do we, what are the dependencies of making the choice of such an orientation? And it turns out that we can define a relation that if you make another choice, then using some Chern-Simons translation form that is also dependent on the multiplicative sequence K that we chose earlier, yeah, that shows up. And okay, and one key observation here is which also makes it different from the smooth theory is that here we need to choose a coherential version, which is a detail that I can maybe explain a little bit more if you want after the talk. But it's something that is different between the smooth theory and the Hodge filter theory, because for smooth theory, if you take a coherential or differential form version, if that makes any sense to you, they will in general be different. But for Hodge filter theories, they are the same. And that makes it much easier, or not much, it makes it possible to define a push forward for a much larger class of maps. Okay, so now you might wonder, how do we choose such a orientation? And okay, for the sake of time, I'm gonna go briefly now through this. So there's an observation due to Karoubi, or maybe it goes longer back, that if you take a holomorphic bundle, then you can choose a so-called bot connection on your bundle. And the condition is that if you express the local transition matrix using forms, then they actually live in the first step of the Hodge filtration. Okay, and that tells us that this KD of our connection is actually in F0 A0, and that means that ED with choosing this extra sigma to be 0 is actually an orientation. And I know that all this notation now maybe doesn't yet make very much sense. So let me just say then that we can use this information that even though the normal bundle of G is in general not holomorphic, but we can nevertheless then, because we define orientation actually as a class in a certain K-theory group, we can think of it as a virtual orientation, and then use this trick in order to get a canonical choice for an orientation. So actually our push forward doesn't depend on the choice of an orientation. That's what I'm trying to say. Okay, and now I get back to it's almost the last slide, I promise. So now we get back to the Abel-Jacobi invariant and the short exact sequence that we studied some time ago. Okay, so now if we start with a proper holomorphic map, so Y is also a complex manifold, then we can associate to its fundamental class in cobordism that lives actually also in this subgroup of MU Hodge classes. Then using our push forward now in this Hodge filter complex theory, we can actually also define a fundamental class there, because that's how you define fundamental class. You take the push forward, or one way of defining fundamental class, you take the push forward of the identity element. Okay, and now we also get an Abel-Jacobi invariant, assuming that the fundamental class of our Y or F vanishes, and then we get an induced invariant in our MU Jacobian. And so in general, we could think of this MU Jacobian as a home for certain secondary invariants. So whenever we have an invariant that vanishes in cobordism, it might have still a non-trivial information in this Jacobian. For example, you could think of secondary Chern classes, but I have not investigated them yet. Okay, and how do you describe this Abel-Jacobi map? And this brings us back to the very beginning of the talk, hopefully, or has some resemblance. So assuming that the fundamental class vanishes in cobordism, that means we can choose some bordism data, just a topological bordism data. And that, what is such a bordism data? Well, we take a map over W, a manifold with boundary over R times X, and then we choose a normal bundle and connection to make it, to enrich it with some geometric information. And then we add a certain Chern-Simons form, which measures, roughly speaking, the failure of the normal bundle of F to be holomorphic. So if F is holomorphic, then we would not have to take care of this guy so much. Okay, and then we can define and construct this Abu-Jacobi invariant, very similar to the very beginning where we evaluated some integral, namely by taking the integral first. So here we take a form omega in a certain step of the Hodge filtration. We pull it back up here in a certain way, and then we smash with this sigma f, take the integral over y, and then we add the integral over where we take whatever lives over the unit interval here, and then evaluate k of this connection from the bordism data and smash with the, or take the wedge with the, no, smash, yeah. We take the product with f upper star of omega. So very similar to the classical formula, in fact. Okay, and that's all I had to say. Sorry for taking too much time.
Questions for Gereon? So I imagine on the one hand, one can look at descendants of MU if one looks at the chromatic perspective homotopy theory. So Brown-Peterson, Morava, K-theory, E-theory, etc. So on the other hand, of course, in your setup, you would need a good tensoring with C. Is that what gets in the way? If you do truncation with the Lazard ring, you start getting primes and so on?
I think that the abstract machinery that I started with, so defining as this homotopy pullback, I think that would work. So that works for any spectrum that you throw in there, and you would also get a similar short exact sequence with the new Jacobian for all these theories. So I don't think you have to have any problem with tensoring with C. So it depends on, like, yeah, what information you can extract from this story. What of course would not work is in most cases would be having a geometric interpretation of these theories. So that's specific to the case MU. Yeah, but the abstract machinery that works for any spectrum that you throw in this.
Yes, of course, yeah. It turns out, of course, as you're saying, the two extremes have geometric information clearly, MU and then chromatic degree 1 K theory, let's say, right? And things in between, it's an open problem to know
so
what
that's,
kind of
but it's a very good question, and so it's very much related to, like, trying to use this theory in order to study phenomena, for example, related to studying complex submanifolds or like obstructions that I mentioned, similar to the Attier-Hirzebruch story. Yeah, so I've been trying with it's like an on and off story, trying to find new examples and trying to get the right obstructions in these theories, but it's a difficult task. Yeah. But I'm still optimistic that there is something out there that you can't find with the other machinery.
Yeah, that's great. Any other questions?
Of course. Hi, yeah, thanks for the nice talk. Maybe along these lines, could you? I was about 1 minute late into the talk. Could you maybe remind me of like the motivation for the construction? It seems, if I look back for the talk, in total, you've shown, if one wishes, a refinement of the Abu-Jacobi map, right? You lifted from something that was defined in the link homology to something in MU. Now, can you say what is it maybe you can do now? Do you now detect something that was previously not detected, or
Yeah, so
what motivated you?
the original motivation was actually to use this new MU Jacobian to detect elements in algebraic cobordism of Levin and Morel, or Morel and Levin. So if you're familiar with this story, so it's a generalization of Chow groups for smooth variety, where you, instead of studying the just subvarieties, you study projective smooth varieties with a projective map to X, similar to cobordism, complex cobordism in topology. So, and this, the obstruction using, so the Atiyah-Hitzbuch obstruction explained using the MU map or the tomorphism, that it goes back to the work of Totaro, who used it in order to find new examples of elements in the Chow group, which vanished in Deligne cohomology, but he could still show that they are non-trivial using his a version of complex cobordism with tensored out and a quotient out in an appropriate way. So the hope was that the Schrodinger's sequence would give us, and this new Deligne cohomology version would give us a new obstruction. And we can actually, so we can find elements in algebraic cobordism that map to 0 in Chow groups, but are still non-zero in Jacobian variant. But they don't reveal, so far, I wasn't able to find an element that reveals some really new geometry along this way, whatever that means. So I wasn't able so far to use this to find new examples that would astonish the experts in complex algebraic geometry. But so with a student of mine, I tried to compute all the ways that, looking at Lie groups and calculating the complex cobordism of these guys, and there we have a way to detect elements in non-trivial elements in the kernel of the homomorphism. But so far we are not able to produce then the correct algebraic variety, or if you want, complex manifold that corresponds to that. So yeah, so far, yeah.
What does this mean, to produce which correct variety?
Yeah, so one thing that you could wonder is, so you look at the tomorphism, and there you have a huge automatic kernel that just comes from that the formal group law in cobordism is the universal one, and the formal group law in cohomology is additive. So there's a lot of stuff that is automatically sent to 0. So you could ask, well, is there anything non-trivial that is not in this obvious kernel? And you can find that also in the cohomology or the cobordism of for Lie groups, but I'm not able to then to show that these elements in complex cobordism are represented by an actual complex manifold or an algebraic variety.
Okay.
Which would be like the most desirable case of an example, I guess. Well, depending on your taste, yeah.
It's a realizability issue.
Sorry.
So it's a realizability issue, like the
yeah, exactly, and so it's also some of them we can reproduce as a smooth manifold, but they are not. You can orient them so they can be complex. Yeah, so there are all kinds of things. So we're still looking for better candidates. But that was the motivation. Going back to your question.
Right, thanks. I see.
Great, thank you. Any other questions? Okay, if not, let's thank Gereon again for giving this talk. Thank you, Gereon. We appreciate it.